Last time, we derived the electric field from continuous charge distributions, infinite line, infinite sheet, and the ring of charge. Those derivations required setting up and evaluating integrals, which can be quite involved. Today, we introduce a powerful shortcut. We'll define the electric flux density vector D, state Gauss's law, one of Maxwell's four equations, and show how it lets us find D and E almost instantly when the charge distribution has symmetry. The electric field E depends on the medium. In free space, it includes the permittivity epsilon 0. To separate the field from the medium, we define a new vector, the electric flux density D. D equals epsilon 0 times E. The units of D are coulombs per square meter, the same units as surface charge density. This is no coincidence, as we'll see with Gauss's law. The electric flux psi through a surface S is defined as the surface integral of d dot ds. In SI units, one line of electric flux starts on +1 coulomb and ends on -1 coulomb. So the total flux is measured in coulombs. The key advantage of D: all the formulas we derived for E from charge distributions still apply, just multiply by epsilon 0. For a point charge, D equals Q over 4 pi r squared. For an infinite line, D equals rho L over 2 pi rho. For an infinite sheet, D equals rho S over 2. Notice that D depends only on charge and geometry, not on the medium. Now for the main result. Gauss's law states the total electric flux through any closed surface equals the total charge enclosed by that surface. In equation form, the closed surface integral of d dot ds equals q enclosed. This is the integral form of Gauss's law. By applying the divergence theorem to the left side, we can convert this to the volume integral of divergence of d dv equals the volume integral of rho v dv. Since this must hold for any volume, the integrands must be equal. This gives us the differential form, also called the point form. Divergence of d equals rho v. This is the first of Maxwell's four equations. It tells us that electric flux diverges from positive charges and converges on negative charges. Three important notes. First, the integral and differential forms are equivalent. They say the same thing in different mathematical languages. Second, Gauss's law is always true, but it's only useful for finding D when the charge distribution has symmetry. Third, when symmetry exists, we choose a Gaussian surface on which D is either constant and normal or tangential, so the integral simplifies dramatically. Let's apply Gauss's law. For a point charge Q at the origin, we choose a spherical Gaussian surface of radius r centered at Q. By spherical symmetry, D has only a radial component, and it's constant on the sphere. So d dot ds becomes dr times the total surface area, dr times 4 pi r squared. Setting this equal to q gives dr equals q over 4 pi r squared. Therefore, d equals q over 4 pi r squared in the ar direction. Exactly what Coulomb's law gives, but derived in two lines instead of an integral. For an infinite line charge rho L along the z-axis, we choose a cylindrical Gaussian surface of radius rho and length L. D has only a rho component by symmetry, and it's constant on the curved surface. The flux through the top and bottom caps is 0. D is tangential there. The flux through the curved surface is d rho times 2 pi rho L. Setting this equal to the enclosed charge rho L times L gives D equals rho L over 2 pi rho in the a rho direction. Again, two lines versus a full integration. That's the power of Gauss's law with symmetry. For an infinite sheet of charge rho s in the z equals 0 plane, we choose a rectangular box. a pillbox centered on the sheet. By symmetry, D points in the plus or minus Z direction and has no component along the sides. The flux exits through the top and bottom faces only. If each face has area A, the total flux is dz times A plus dz times A equals 2 dZA. The enclosed charge is rho s times A. So dz equals rho s over 2, and d equals rho s over 2 in the AN direction. One line of algebra. Now consider a uniformly charged sphere of radius a with volume charge density ρ0. We need two Gaussian surfaces. For r less than or equal to a inside the sphere, we use a spherical surface of radius r. The enclosed charge is ρ0 times 4/3 pi r cubed. Gauss's law gives dr times 4 pi r squared equals ρ0 times 4/3 pi r cubed. So d equals ρ0 r over 3 in the AR direction. The field grows linearly inside. For r greater than or equal to a, outside the sphere, the enclosed charge is the total charge q equals ρ0 times 4/3 pi a cubed. So d equals ρ0 a cubed over 3r squared in the AR direction. Outside, it looks like a point charge as expected. Let's recap today's key ideas. D equals epsilon 0 E. The electric flux density removes the medium dependence. Gauss's law in integral form. The closed surface integral of d dot ds equals q enclosed. In differential form, divergence of d equals rho v. This is Maxwell's first equation. When symmetry exists, spherical, cylindrical, or planar, Gauss's law gives us d in one or two lines of algebra, replacing lengthy integrations. Next time, we'll introduce the electric potential V, which gives us yet another way to find E and connects energy to the electric field.